Good morning, sir.
Good morning.
Good morning, sir.
Good morning. So, is my screen visible?
Yes, sir.
Yes, sir.
Yeah. Okay. So, are there any questions, doubts?
Sir,
Yeah.
when we talked in this for uh, in the first method for shear locking to avoid shear
Yeah.
locking, we got talked about spurious modes. So, sir,
Yeah.
can we understand them like with any physical sense? What exactly are those? Because like in the 12 eigenvalue that eigenvalue problem, if 3 were 0, that would signify rigid body mode. So what
Yeah.
would other 0 would signify, like what exactly it is?
They are not the no they are although their eigenvalues are zero, but they are not ideally only the eigenvalues should be zero corresponding to rigid body modes. But because of this under integration of the stiffness, you get some zero eigenvalues corresponding to modes which are not representing rigid body modes, but still the eigenvalues are zero. So they are that is what we refer to them as spurious modes. So they will be no will give you, say if you have assembly of elements, it will give you zigzag displacement distribution.
Okay,
So one element positive, other element negative, positive, negative, positive, like zigzag pattern.
okay, that, okay. That the displacement field will be like that.
Yeah, it will be zigzag. So they are not rigid body modes, but the eigenvalues are zero.
Okay, sir. Okay.
So it will be zigzag, no? So one, of course, say in one node the displacement is positive, other node displacement would be negative, alternately. So it kind of a zigzag pattern.
That's why we are saying it. These are zero energy modes.
Yeah, they are eigenvalue is zero, but they are referred to as spurious modes or hourglass modes.
Okay, okay, sir. Thank you, sir.
Okay. Anybody? Any other question? Okay, so if there are no questions, so let me start. So today I'm going to discuss the third approach of overcoming this transverse shear locking. So that is third approach I had mentioned was modified interpolation functions. So in this the third approach, I'm not able to write on the screen, so let me close and open it again. So is the screen visible? Hello.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Okay. So the third approach to eliminate this transverse shear locking is, as I had mentioned, is the modified interpolation for. So I just write interpolation for theta x and theta y in gamma xz and gamma yz. So this is also known as field consistent approach in the literature. Field consistent approach. So what it means is that now if you look at let's say a four noded isoparametric element, plate bending element. So we have x and y, and the element is arbitrary quadrilateral in the physical coordinate space, and this is mapped to a square in the natural coordinate space, xi and eta. So in this we have seen that the normal approach is to write gamma xz as del w by del x plus theta x, and which is written as I going from 1 to 4 del ni by del x into wi plus I going from 1 to 4 and I into theta xi. So this is how the normal way we write. No, but this is what if it is used for thin plate problems, it gives rise to locking. So theta y. So this is also written as I going from 1 to 4 del ni by del y into wi plus I going from 1 to 4. Although you can use actually index notation, and you can simply write it as del ni by del y into wi plus ni into theta xi, but I am still using the summation ni into theta yi. So in the field consistent approach, what we want to do is because here no, from the w we are having the derivative term, so whatever is the highest power of x or y in ni, the del ni by del x or del ni by del y would be one power lower, 1 degree lower. So this ni and ni used for the interpolation of theta x and theta y should be modified, and we should use the modified functions which are one order lower compared to no ni's, original ni's, and that is they should be similar to del ni by del x and del ni by del y. So that is what is known as the this modified interpolation for theta x and theta y in gamma xz and gamma yz. So let me take two cases for this to demonstrate the exactly what are these modified functions, how to get them. So first case I am taking case 1, when the element is a rectangle in the physical coordinate space. So element is a rectangle in the physical coordinate space. Yeah, there is some problem, I'm not able to write again. So let me close this and open it again. Yeah, so yeah, I had closed the screen in between. So is it visible again?
Yes, sir.
Okay. So first case I am taking the element is a rectangle in the physical coordinate space. Physical coordinate space. So no, this simplifies the development of the modified shape function. So that is why I am discussing first this case. So here what I am saying is that no, you have element in the xy space. So say the element is a rectangle, and these are the nodes 1, 2, 3, and 4. The coordinates are x1, y1. The coordinates of node 2 are x2 plus a, and y2. No, it will be y2 is equal to y1 because it is rectangle. So this is y1, and this will be,
Sir,
this is
x1 plus
also, yeah, x1 plus a, that is right. So x1 plus a, y1, and then this will be x1 plus a, y1 plus b, and the fourth node is x1 and y1 plus b. So these are the coordinates of the element. So now for this case, if you look at the Jacobian matrix, if the element is a rectangle in the physical coordinate space, that is edges of the elemental are parallel to x and y axes. So when we look at the Jacobian matrix, we, of course, by definition, that is del x by del xi, del y by del xi, del x by del eta, del y by del eta, and this you can see the x is summation no ni xi and y is summation ni yi. So if you put the coordinates and then differentiate with respect to xi and eta, that exercise you can do yourself. So you will find that the Jacobian matrix would be a by 2 0 0 and b by 2. So this is what the Jacobian matrix would be there. And now if you look at the J inverse, so the J inverse would be simply 2 by a 0 0 and 2 by b. So this will be J inverse, that is inverse of this matrix. Okay. So now if you look at the derivative of the shape functions with respect to x, so del ni by del x would be, we know that it is j11 star into del ni by del xi plus j12 star into del ni by del eta. And since now the j12 star is 0 and j11 star is 2 by a, so this is simply 2 by a into del ni by del xi. And similarly, if you look at the derivative of say functions with respect to y, so del ni by del y, we know that it is j21 star into j21 star into del ni by del xi plus j22 star into del ni by del eta. So again j21 star is 0 and j22 star is 2 by b. So this would be 2 by b del ni by del eta. So now this is the derivatives of the shape function. So now in the shear strain we have no del ni by del x into wi plus we have ni into theta xi. So we want to, instead of using ni for the interpolation of theta x and theta y in the interpolation of shear strains, transverse shear strains gamma xz gamma yz, we want to use the shape function which is in form it is similar to this del ni by del zeta, and similarly for the theta y we want to use the modified shape function which is similar to del ni by del eta in form. So that is what is the modified interpolation functions. So based on this we say that we interpolate transverse shear strains using modified interpolation for theta x and theta y. So that is what I am saying, that rather gamma xz we would write as del w by del x plus theta x. So when we use the interpolation, we want to write that as I going from 1 to 4 del ni by del x into wi. But for now theta x we use modified interpolation function. So let us say that modified interpolation function is ni bar. So now this is a different function, theta xi, and similarly the gamma yz is written as which is del w by del y plus theta y. That the first term is same, whatever we get from the the original interpolation of w, so del ni by del y into wi. But for theta y in this expression I is equal to 1 to 4, we write this as ni double bar into theta yi. So now here these no we use these ni bar and ni double bar are the modified interpolation functions. So here ni bar is a modified interpolation function consistent with modified interpolation function or shape function, whatever you want to call, interpolation function consistent with del ni by del xi. So why I am saying that? Because no, we have seen that in the strain del ni by del x is equal to actually del ni by in terms of del ni by del zeta del xi. So no, the interpolation of theta x should be also similar to del ni by del xi. And in the interpolation of gamma yz, we have del ni by del y as del ni by del eta. So the interpolation of theta y should be similar in form to this del ni by del eta. So that is what I am saying, that ni bar is a modified interpolation function consistent with del ni by del xi, and ni double bar is a modified interpolation function consistent with del ni by del eta. So now what we,
Sir,
yeah,
can you repeat this? It was NY bar, NI bar, right? Uh,
yeah, ni bar and ni double bar.
so gamma xz equals to NI bar theta xi, or
Yeah,
NI double bar theta xi.
ni bar theta xi, and gamma in gamma yz we have ni double bar into theta yi.
Okay.
Yeah, this one. So here, no, in the gamma xz we have ni bar into theta xi, and in the gamma yz we have ni double bar into theta yi. So these two modified interpolation functions would be different because ni bar is similar in form to del ni by del zeta xi, and ni double bar is similar to del ni by del eta. So now if you look at the first the derivatives itself, so now we are talking of course discussing the four noded element. So if you look at the del n1 by del xi, now we look at the form. So we have all, the expression for n1 for a four noded element. So if we differentiate that with respect to xi, we will get actually minus 1 by 4 into 1 minus eta. And if you differentiate n1 with respect to eta, so that would come out as minus 1 by 4 into 1 minus xi. Similarly, now you can look at the all the four no shape functions, original shape function. So del n2 by del xi would be 1 by 4, 1 plus eta, no 1 minus eta, not plus, 1 minus eta, and del n2 by del eta is minus 1 by 4, 1 plus xi. So now these are the derivative, that means the derivatives of the shape functions for four noded isoparametric element with respect to xi are basically only having constant term and linear term in eta, and the derivatives of the shape functions with respect to eta have constant term and a linear term in xi. So basically the this means that the modified shape functions, that is the modified shape functions are interpolation functions. So the modified shape functions. And now if we look at the ni bar, so this should be ni bar is going with gamma xz, where del ni by del xi is there. So this should be linear in eta and constant along xi. And when you look at ni double bar, so this should be linear in xi and constant along eta. So now if you look at the actually forms of ni bar and Ni double bar. So you will no, because as I already stated, Ni bar should be linear in eta and constant along xi. So for example, if I write n1 bar, so n1 bar would be a naught, say some a naught and a1 are constants. So a naught plus a1 eta, it should be linear in eta. And similarly, now that you can write all other four. So n2 bar would be say b naught plus b1 into eta. N3 bar would be c naught plus c1 into eta, and N4 bar would be d naught plus d1 into eta. And when we look at the N1 double bar, which goes to interpolate theta y in gamma yz, that would be again having a constant term and linear term in xi. So E1 plus E0 plus E1 xi. E0 and E1, these are constants. So similarly, N2 double bar would be F0 plus F1 into xi. N3 double bar would be G naught plus G1 into xi, and N4 double bar would be H naught plus H1 into xi. So this is the form of the interpolation functions. So now these kind of shape functions be used to interpolate the theta x and theta y in the transverse shear strains. So that is the above modified shape functions Ni bar and Ni double bar are used. Now these are the interpolation of theta x and theta y only for gamma xz and gamma yz. But when you look at the curvature tensor, so in that you have theta x and derivatives of theta x and theta y. There we use the original shape function, the derivatives of the original shape function. So the above modified shape functions Ni bar and Ni double bar are used only in transverse shear strain interpolation. Are used only in transverse shear strain interpolation. Now the question is, what are these? No, the shape functions. We should not have any unknowns ultimately. So we have these constants a naught, a1, b naught, b1, etc. So how do we find these? So there is a way to get that. So next question arises: how do we get? How to get a naught, a1, and all these constants? So that's the question. How do we get these? So it's straightforward. It is these are obtained by minimizing the difference between the original shape functions and the modified shape functions. So the constants a naught, a1, etc. are obtained by minimizing the difference, minimizing the difference between original and modified shape functions. And how we do that? How do we minimize the difference? So for minimizing the difference, we use what is known as method of least squares. Modified shape functions using method of least square. Method of least squares. So this is how we get these constants which we have got in the modified interpolation function. So let me know. So what I am saying here is saying that minimize, and the difference is the integrated over the element domain in the natural coordinate space. So that is ni is the original shape function minus ni bar is, let's say, the modified shape function. We take the square of this and then integrate it over the natural coordinate domain of the element, and we minimize this. So see, here under the unknowns are ni is a known shape function, the original shape function. If it is a 4 noded element, then for that. If it is 8 noded elements, then for that. And ni bar has got unknown constants. So ultimately this integral is going to be function of those unknown constants. So the first order necessary condition for that is the derivative of the this integral with respect to the unknown constant should be equal to 0. So this is equivalent to saying that del, let's say if I look at the n1 bar, so for n1 bar del by del a naught of integral minus 1 to plus 1 minus 1 to plus 1, n1 is the shape function, and n1 bar is a naught plus a1 eta, so it is minus. So we write here that as minus, so minus a1 into eta, and then square this difference and integrate it over the entire domain, and then differentiate it with respect to a naught and put it equal to 0. So that's the first order necessary condition for this to be having minimum. So now if you do this, so you will find that we can take this differentiation inside the integration sign. So minus 1 to plus 1, and then this will be first be it is square, so twice of n1 minus a naught minus a1 into eta, and then the derivative of this with respect to a naught, so that is equal to minus 1, and then d high d eta is equal to 0. So this minus 2 we can take as common and divide both left hand side and the right hand side. So finally this equation comes out as integration minus 1 to plus 1 minus 1 to plus 1 n1 minus a naught minus a1 into eta, and then into d high d eta is equal to 0. So let us say that this is equation 1. I will refer it later. So similarly, there are two unknown constants. So another equation would be del by del a1 of minus 1 to plus 1 minus 1 to plus 1, and then we will have n1 minus a0 minus a1 into eta whole square d high d eta is equal to 0. So that's the first order, second first order necessary condition. And if we take the differentiation inside the integration sign, so we will get minus 1 to plus 1 minus 1 to plus 1, and then twice of n1 minus a naught minus a1 into eta, and then the derivative of this with respect to a1, so which will give you minus eta, and this is d high d eta equal to 0. Again minus 2 you can take common and divide the whole expression. So ultimately you can write this equation as integration from minus 1 to plus 1 integration from minus 1 to plus 1, and then we will have n1 minus a0 minus a1 into eta d high. We cannot divide of course by eta, no, so because that's the we are doing the integration with respect to that, so we can, if we have any constant, that we can divide by that but not by eta. d high d eta equal to 0. So this is the second equation too. So now for finding out n1 bar, we have this equation and we have this equation. So from by solving these two equations we can get a naught and a1, and once we have a naught and a1, then we have our n1 bar. So to get that, now you need to evaluate these integrals. So integral minus 1 to plus 1 minus 1 to plus 1, we need to evaluate n1 d high d eta, and this is nothing but the integral n1 is nothing but 1 by 4 1 minus xi minus eta plus xi eta. The expression for n1, so you can write it in this form and then integrate this. So if you integrate this, no, the first term integration would be xi and eta when you put the limits. So 1 minus minus 1 and 1 into 1 minus minus 1, so that will give you 4. The integral of this will be xi square by 2 into eta when you put the limit, so this will go to 0. Integral of this would be xi into eta square by 2, and when you put the limits of eta, this term would be 0. The integral of this term would be xi square eta square by 4. When you put the limits, it would be 0. So ultimately you will find that this integral is just going to be unity. So now if you look at the the other integrals, for example, now this is a n1 integration. So when I look at this equation, so integration of n1 is basically 1, and when you look at the integration of this minus a naught is constant, so that will also be basically xi and eta. So when you put the limits, it would be 4, and when you look at this term, the integral would be xi eta square by 2, and when you put the limits of eta from -1 to +1, this term would be 0. So finally you would see that equation 1 can be simply written as 1 minus 4a naught is equal to 0. So that will give you a naught is equal to 1 by 4. And then we need to know now the from second equation we have to find this a1 now from the second equation. In the second equation, if you look at, we have the integral one term is integral n1 into eta. So we need to evaluate this integral -1 to +1 -1 to +1 n1 into eta d is high d eta. So you will see that this integral -1 to +1 -1 to +1 1 by 4, and multiply this n1 with eta. So it would be eta minus xi eta minus eta square plus xi eta square d high d eta, if you put the values. And if you do this integral, you will again find that no, this integral would be 0 because it would be xi eta square by 2. When you put the limits of eta, it would be 0. This term will also be 0 due to xi. This term also would be 0, only this integral would be non-zero. So integral of minus eta square would be minus eta cube by 3, and when you put the limits -1 to +1, you will get basically minus 2 by 3 minus 2 by 3. No, and you have xi also. So that will give you basically limits -1 -1, so that is 2. So we will get 4 by 3. 4 by 3, when we divide by this 4, so we will get that as -1 by 3. So it's a simple integration. Now you can actually do this explicit integration. And if you see now again, if you look at the integration of now a naught into eta is there. So if you look at this, integral would be xi into eta square by 2, and because of the limits of eta square, it would be 0. So you will have only this as non-zero. So the integral of this is going to be minus a1 eta cube by 3 into xi, and when you put the limits, so you will see that equation 2, you can check yourself that equation 2 can be written as -1 by 3 minus 2 by 3 into 2a1 equal to 0. So you will find here that a1 would be -1 by 4. So that means now if you look at your n1 bar, so n1 bar is 1 by 4, because both a naught and a1 are a naught is 1 by 4, a1 is -1 by 4, so we take 1 by 4 common, so we get 1 minus eta. So this is n1 bar. So similarly, now you can derive the n2 bar, n3 bar, n4 bar, and similarly n1 double bar, n2 double bar, and so on. So if you do that same procedure which I just have shown for n1 bar, you can get n2 bar will come out as 1 by 4 1 minus eta, so same as n1 bar. N3 bar will be 1 by 4 1 plus eta, and you will find that n4 bar will be equal to 1 by 4 1 plus eta. So similarly, when you get know your n1 double bar, that will be equal to 1 by 4 1 minus xi, and n2 double bar is 1 by 4 1 plus xi, and n3 double bar will come out as 1 by 4 1 plus xi, and n4 double bar will be 1 by 4 1 minus xi. So these are the modified interpolation functions. So in the interpolation of gamma xz and gamma yz, for substituting for interpolating theta x and theta y, you use these functions for theta x in gamma xz, and you use these interpolation functions for theta y in gamma yz. And if you do that, you will find the element will work for both thick and thin plate problems. It will give you accurate results. There would be no spurious modes, and you will get the correct results for thick and thin, both kind of problems. So you can use the same element whether the plate is thick or thin. So let me write just what I spoke. If we use the above modified shape functions, the element will be free from locking. Will be free from locking. The element when it is free from locking, so that means the element predicts correct results for thick and thin plates. For thick and thin plates. Now you will know when you are using modified shape functions. So when you are integrating the various terms to find out the stiffness, so you integrate all of them using the full integration. You don't use any reduced or selective integration. So in this, all the stiffness terms are evaluated using full integration. Full integration, as per the highest power of xi and eta in the integrand, you use the number of Gauss points. And I have already mentioned earlier that so you note that curvature terms, that is the bending stiffness terms, curvature terms are interpolated using derivatives of original shape functions. So this is one. Now let me now what if the element is actually arbitrary quadrilateral in the physical coordinate space. So this is what I demonstrated, is if the element is a rectangle in the physical coordinate space. So now the case 2 is the element is not a rectangle. Element is not a rectangle in the physical coordinate space. Physical coordinate space. So hello, am I audible? Yeah, hello, am I audible?
Yes, sir, you're audible.
Yes, sir.
Yes,
Okay,
sir.
okay. So yeah, now the case 2 I am talking about is for the element is not a rectangle in the physical coordinate space. So that means it is arbitrary quadrilateral. So say we have x and y, and these are the nodes 1, 2, 3, and 4, and it is mapped to a square, of course, in the natural coordinate space. So we have this xi and eta. These are the nodes 1, 2, 3, and 4. So now what do we do in this case? So see, we need to make use of actually the Jacobian and inverse of the Jacobian to tackle this problem. So we already know. So I have already talked about that. So we know that. So we are going to use these relations. So that is why I am writing. We know that del by del xi and del by del eta are given by the in terms of Jacobian matrix J11, J12, J21 and J22. J11 is del x by del xi, J12 is del y by del xi, J21 is del x by del eta, and J22 is del y by del eta into del by del x and del by del y. And the inverse relationship also we know. So the inverse relationship is del by del x, del by del y is equal to inverse of Jacobian matrix. So let us say those are J11 star, J12 star, J21 star, J22 star. Now this is del by del xi and del by del eta. So this relationship we actually know. So now what we do is, if the element is an arbitrary quadrilateral, so in that case you will find that del ni by del x will be in terms of both xi and eta. Similarly, del ni by del y would be both in terms of del ni by del xi and del ni by del eta. So we have to take care of that. So for that purpose we introduce what are known as pseudo transverse shear strengths in natural coordinate space. Why pseudo? Because we actually define the physically actual transverse shear strengths are defined in the physical coordinate space. So whatever we define in the natural coordinate space, that we are referring to as pseudo. So we call as pseudo transverse shear strengths, transverse shear strengths in natural coordinate space. So that is the one is gamma. Now instead of talking about directly gamma xz and gamma yz, I am talking about this gamma xi z. So gamma xi z we define in place of x we are using xi. So it would be del w by del xi plus theta xi. Theta xi is the rotation about positive eta axis, and this can be written as per the, if you use, now we are going to, for theta xi we will use the interpolation which is in form similar to del ni by del xi. So we will use summation I going from 1 to 4 del ni by del xi, because del w by del xi would be simply del ni by del xi into wi, and then plus for the interpolation of theta xi. Now I am talking about theta xi, which is the rotation about theta axis. So I go equal to 1 to 4, and for this we use the interpolation function ni bar. Ni bar is similar to what we did, same as what we did in the case 1, because that is, ni bar is consistent with del ni by del zeta, and here in the gamma xi z we have del ni by del xi. So ni bar should be in form should be same as del ni by del xi. So we are using ni bar into theta xi I. And similarly we define gamma eta z. Gamma eta z is now del w by del eta plus theta eta. Theta eta is rotation about negative xi axis, similar to the way we interpreted theta x and theta y. So this will be I equal to 1 to 4 del ni by del eta into wi, and then plus the interpolation of theta eta. The shape function should be consistent with del ni by del eta. So we use ni double bar here into theta eta I. And of course the theta xi I and theta eta I are the values of theta xi and theta eta at the ith node. So no, of course the node going from 1 to 4. So now here these shape functions ni bar and ni double bar are modified shape functions, are, so we have already said modified shape functions, and they are same as derived in case 1, same as derived in case 1. So ultimately, of course, see, when we were developing the elementable governing equation, we have to look at the strain energy for the functional. and in the strain energy functional we need gamma xz and gamma yz. So we interpolate gamma xi z and gamma eta z using the modified interpolation functions ni bar and ni double bar, and then we want to write gamma xz and gamma yz in terms of basically this gamma xi z and gamma eta z. So because ultimately that is what we need to substitute in the strain energy strain energy function. So we need to express, and why we are not taking this form, because it is easier to write, no way, when we are writing it in this form, it is easier to write ni bar, and similarly when we write it in this form, it is easier to write ni double bar. So that is why we are starting from there, and then we need to express gamma xz and gamma yz in terms of gamma xi z and gamma eta z using the Jacobian relation which we have already discussed, using Jacobian transformation. So let me first demonstrate how do we write say the gamma xz. So the gamma xz we are going to write. So now see the way we write the derivatives, del by del x. See in this, del by del x is written as j11 star into del by del xi plus j12 star into del by del eta. So same way we want to write gamma xz using this relation gamma xz as j11 star into gamma xi z plus j12 star into gamma eta z. So we want to make use of the same kind of a relationship. So we use gamma xz is equal to j11 star into gamma xi z plus j12 star into gamma eta z. And now we know that if we substitute gamma xi z and gamma eta z, I want to simplify this so that we can use it in programming. So j11 star of course is there as it is, and then we have gamma xi z, which is I going from 1 to 4 del ni by del xi into wi plus I equal to 1 to 4 ni bar and theta xi I. So this is now the first term, and plus we have j12 star. So in this we substitute gamma eta z, and gamma eta z is I equal to 1 to 4 del ni by del eta into wi plus I going from 1 to 4 ni double bar theta eta I. So this is what you can actually write this. And so now you have gamma xz expression, and this you can simplify. So you would see the gamma xz. Now you collect the wi terms together. So if you collect the wi terms together, so you can write this as I going from 1 to 4, and the first term is j11 star I'm taking inside the summation. So j11 star into del ni by del xi plus j12 star into del ni by del eta. So that's the first term into wi, and of course the other terms are as it is, j11 star summation I going from 1 to 4 ni bar theta xi I, and plus j12 star summation I going from 1 to 4 ni double bar theta eta I. So those remain as it is. So now if you see, you can say that gamma xz, now this is what? So this is nothing but, if you see, it is actually del n1 by del x. So the first term again reduces to the same form, that is I going from 1 to 4 del ni by del x into wi. So this is same what we used earlier, but now we have these ultimately see, we want to have physical degrees of freedom, the rotations about x axis and y axis. So in these expressions we need to express theta xi I and theta eta I in terms of theta xi and theta yi. So that's the another thing we need to do. So let me write this as j1 star summation I going from 1 to 4 ni bar into theta xi I plus uh, yeah, plus you have j12 star summation ni double bar theta eta I. So these terms are there. Now what we do, again making use of no, the way we have this no relationship, yeah, this relationship. So here this gives the derivative of with respect to xi eta in terms of derivative with respect to x and y. So same thing we use no, for the theta xi and theta eta, no, the same kind of a relationship, although this relationship is for the derivative operators, but we use the same relationship for theta xi and theta eta. So we write, we write theta xi I, we want to express it in terms of theta xi and theta yi as j11 I. Now these are the nodal values, so the elements of the Jacobian matrix have to be evaluated at nodes. So j11 I means j11 at node I into theta xi plus j12 I into theta yi, and similarly theta eta I is written as j21 I into theta xi plus j22 I into theta yi. So now substituting this, you can actually write, so if you see finally this gamma xz can be written as the first term remains as it is, no, I going from 1 to 4 del n I by del x into wi, but the other terms become, now we have j11 star and summation I going from 1 to 4, and we have this ni bar, and then we have theta xi I, and theta xi I is written as j11 at ith node into theta xi plus j12 plus j12 I into theta yi, and plus the other term j12 star into I going from 1 to 4 ni double bar, and then theta eta I, and theta eta I is written as j2 I into theta xi plus j22 I into theta yi. So this is how you write these. And so now you can say that gamma xz, let us simplify it further. So I going from 1 to 4 del n I by del x into wi, and plus let us collect the theta xi terms together and theta yi terms together so that we can get the modified shape functions for this case. So you would write this as summation I going from 1 to 4, and theta xi terms I am collecting together, so we will have j11 star into j11 I into ni bar, plus we will have j12 star into j21 I into ni double bar, and this goes with theta xi, and plus you have same way I equal to 1 to 4, and then we collect the terms of theta yi, so that is j11 star into j12 I into ni bar, and plus we have now this j12 star into j22 I into ni double bar into theta yi. So yeah, so j11 j12 I ni bar j12 star j22 I. So you will notice now here there are two kind of things. Now like if you look at del ni by del x will be function of xi and eta, j11 star would be function of xi and eta, but j11 I is a constant because this is the value of j11 at node I, and of course ni bar is in general a function of xi and eta. So same way you can look at, so the j values at I means they are the evaluated at node, so they are constant values, whereas the other terms are functions of xi and eta. So you can ultimately write this gamma xz as summation I going from 1 to 4 del ni by del x into wi, and plus this is I going from 1 to 4, and let me call that as this as, let us say, m11 theta xi, and plus I going from 1 to 4 m12 theta yi. So that means what I am saying is this whole term I am calling as m11i, and this whole term, this I am calling as m12i. So these are the shape functions, now modified shape functions to be used for interpolating the transverse shear strains for an element which is arbitrary quadrilateral in the physical coordinate space. So similarly, now the same derivation approach you can now do and write. You would be able to write gamma yz is equal to summation I going from 1 to 4 del ni by del y into wi, and plus we will have I going from 1 to 4, and then we will have j21 star into j11 into ni bar, plus we will have j22 star j21 I into ni double bar into, you will have there theta xi, plus we will have summation I going from 1 to 4, and then we will have j21 star j12 ni bar. You can derive this the way I did for gamma xz, so you can cross check this derivation, this expression j22 star j22 ni double bar into theta yi, yeah, theta yi over here. So this also you can write gamma yz is equal to summation I going from 1 to 4, the del ni by del y into wi, plus summation I going from 1 to 4. This I am calling as m21 theta xi, plus summation I going from 1 to 4 m22 into theta yi. So this whole term I am calling as m21 and this whole term I am calling as m22. So you can write it like this. Now we have, I have already explained you what are m11 m12. So you can see that where I will write just one, and then no, similarly I have already explained you that what are these. So m11 is j11 star into j11 into ni bar, plus j12 star into j21 into ni double bar, and like that, no, you can write m12 you can write m21 and you can write m22. So similar way, no, I have already explained you that what are these. So now once you get this, so then comes finally, what would be the form of BS matrix for the interpolation of transverse shear strain, gamma, which is in terms of gamma xz and gamma yz. So this will be, you can write this will be equal to the matrix here and the nodal degrees of freedom, and the nodal degrees of freedom are same. So if you look at w1 theta x1, let me, so you have w1 theta x1 theta y1, w2 theta x2 theta y2, finally theta y4. So this is the vector of elemental degrees of freedom. So now if you look at, so gamma xz is going to be del n1 by del x, and then you have theta x term also, theta y term also. So we will have m111, so that is m11 at node 1, and we will have m12 at 1, and then you will have del n2 by del x, and then you will have M11 at node 2, you will have M12 at node 2, and similarly del N3 by del X, and M11 at node 3, M12 at node 3, and similarly, the last one you can write. Similarly, the gamma YZ would be del N1 by del Y, and M211, M221, del N2 by del Y, M212, M222. So subscript to subscript is node number, del N3 by del Y, and M213, M223, and so on. So you can write that. And so therefore this is Bs into De. So this will go in defining your transverse shear part of the stiffness matrix. So this Bs you will use. So instead of what we talked about earlier, you will use this Bs, and if you do this, you develop the element in this manner. It would be locking free and will predict the results for thick and thin, both kind of problems. So I think this is where I want to stop. And if you have any questions and doubts, you can ask. Hello. So yes, are there any questions, doubts?
Sir, which book we can follow for this particular part?
Yeah, this part is actually you can find in the, I think that book you may not find. So there is a finite element book by G Pratap, or you can find the research paper. So if you in the Science Direct, if you search field consistent and G Pratap, G Gangan and Pratap, Prathap, Pratap. If you search in the Science Direct, you will find the papers. So there is a paper on the 8-noded, 4-noded finite elements to formulate this. So of course this is not available in J.N. Reddy, or it's not available in Asghar Bhatti. It's available in book by Gangan Pratap, and also the papers written by him. But I have given you all the essential steps involved in the whole of the derivation. So and of course this element based on mostly in the packages. If you look at the ANSYS or Abacus, so in the packages you have elements which are based on the first approach for eliminating shear locking, that is actually reduced or selective integration. So in the packages you have only those elements. In the packages you won't find elements based on consistent interpolation. The second approach I discussed are the elements based on modified interpolation. So of course there are some elements based on mixed interpolation. No, the gamma xz and gamma yz are interpolated independently. So the somewhat similar things are available. But most of the packages you will have the first approach based elements. So hello, are there any questions? Further questions?
Sir,
Anybody?
I have
Yeah,
doubt previous class.
yeah,
Sir, can I?
yeah. You can ask. Yes.
Yes, sir. Sir, I was going through the like classical plate theory,
Okay.
and there, sir, like there was one term F in E, like apart from external term and the like stiffness
Yeah,
term, there was
external
one more
force,
term.
there is an internal load. Because when we talk of element, one particular element, so it no along adjacent of that element there would be other elements. So whatever forces as a reactions are coming on that element, we are representing that by F in E. That is F internal for the element.
Yes, sir. Sir,
Yeah,
sir,
yeah.
there we are finding del W by del N, right?
Del W by
Del N, like
no, del W by del N, and del W by del no, I would have written del W by del N and del W by del T.
sir,
So
actually
those
in
are,
yes, sir. Sir, so
yeah.
how to evaluate this? Actually, I was working on the assignment, and
No, for actually ultimately when you are solving problems, so see, you don't have to evaluate F internal actually explicitly. What is done is when you have, I know there would be some F internal, and when you assemble, So when you two element boundaries are there, so these, because internal forces are going to be equal and opposite, so they cancel out.
Okay.
And at the boundaries, either these internal forces are zero or the corresponding primary variables are zero. So there
Okay.
also, for solving for the displacement, you don't need F internal. So you can just work with the stiffness matrix and F external, because when you
Yes.
are ultimately imposing the boundary condition and solving the problem, so when you are solving for the unknown degrees of freedom, that would require only know the assembled part, know that part assembled, and after eliminating rows and columns, that part of the stiffness matrix and the external load vector. You don't need F internal. So actually you
Yes, sir.
don't need that.
Yes, sir. Sir, my question was like somewhere I read that, like suppose if in the internal nodes, like if we
Yeah,
apply moment or force, so
yeah.
in that case, I think there will be some elements in this.
Yeah,
But
if there is a concentrated force or a moment is applied, so then in the corresponding degree of freedom, whatever sum of the internal forces would be there, that would be equal to this externally applied force or a moment. So you just in the corresponding row, you add that force or a moment.
okay, sir.
So I think this we discuss usually in the, I think the way I discussed, no, the one example I took for the truss element. So there I said, when we take the equilibrium equation for a node, so there the internal forces were expressed in terms of the external load. So ultimately you can replace there these internal forces in terms of the external forces if they are non-zero in the corresponding degree of freedom.
Okay, sir. And sir, one more
Yeah.
doubt. While writing the code, can we use the inbuilt function of like differentiation integration directly,
Yeah,
or
you can
do
use.
we have
Yeah,
to?
you can. No,
Okay.
you can use the MATLAB inbuilt functions for differentiation and integration.
Okay, sir.
Yeah,
Okay, sir. Thank you.
yeah. Okay, okay. Anybody else? Any question? Others? Are there any questions? So if there are no questions, I'm stopping. Thank you all for your attention. Thank you.